All right, guys, welcome to our next video in physics here. This time, we're going to look a little bit more at energy by itself. When we talk about work, that's kind of it's not so much a type of energy, it is just a transfer of energy. But today we're going to look at different types of energy and get really specific on potential energy and how we can go about calculating that and what kind of information we can get from that, right? So to start out with, just kind of some review of stuff you guys probably know from previous science courses, is that there's lots of different types of energy on the planet. And remember, just energy is just the ability to get something done. And so there's lots of different ways that we can get things done, right? But we can actually break all energy up into one of two categories, okay? So the types of energy you guys should know are things like gravitational, chemical, nuclear, heat, light, sound, electricity. You may not know elastic energy so well, but that's okay. So to go through this here, potential energy is basically any type of stored energy. We're going to talk a lot about that today. Types of stored energy are all the ones that we have on the left here. So elastic, gravitational, chemical, nuclear. It's energy stored in some way, shape, or form. So these four ones that we've listed here, those are ways we can store energy. Elastic potential energy is when we stretch something out. It's something that wants to return back to its original shape. That always creates elastic energy when we get it out of its original shape. Something like a diving board, an elastic band, a bow and arrow, anything that you have to like pull back or stretch out or compress that wants to jump back to where it is, that's a form of elastic energy, right? The fact that we've like stretched it out, at that point what we've done is we've given it energy, and it's the energy to snap back into place. The main type of energy in terms of potential that we want to talk about is gravitational potential energy, which is how much energy something has just from being up high off the Earth's surface. All right? Heavier things and things that are higher up tend to have more gravitational energy than something closer to the ground or lighter. All right? So it's basically how much energy something has just because of its position in space. Chemical potential energy, we actually talked about back in chemistry. It is the energy that holds bonds together. All right, so it is if we break those bonds apart, we release that energy. And then nuclear energy is energy stored, or that's stored in the nucleus of an atom that we can then split apart. Basically, it's the energy holding all those protons and neutrons together. Okay, kinetic energy is the energy that moving things have. All right, and so depending on what's moving and how it's moving, that's kind of how we classify the different types of kinetic energy. All right, so heat is actually a type of kinetic energy. Heat comes about when particles start vibrating faster and faster and faster. It creates heat, so that's what we think of as, so because it's heat generated through motion, that's why it's kinetic energy. Light is just the movement of photons, sound is the movement of air waves, and electricity is the movement of electrons. So all those things are types of kinetic energy that have to do with motion. Now, we can convert between one type of energy and another, and in particular, what we're going to be looking at a lot in this physics course next week is how we can switch between potential and kinetic energy, all right? We know that this happens. If I have something that I've lifted up, I've given it potential energy. If I then drop it, that potential energy gets turned into kinetic energy as that thing speeds up and speeds up and speeds up and as it falls down. So because things tend to have both potential and kinetic energy at the same time, we can actually group these two things together and measure how much energy something has through what we call mechanical energy, which we'll look at next week, okay? So mechanical energy is not its own type of energy. It is just a combination of all of the potential and kinetic energy that an object possesses based on either where it is and how it's moving. All right, so let's take a closer look at potential energy. Now, the descriptions I'm giving you today, they're all already in your notes on page 6. It's kind of a lot to read, though. So if you do want to know more information, or if you're a little bit confused about what potential energy is, there's a good set of notes on page 6 of your booklet that kind of walk you through all the different types of energy, of potential energy. But one more time, potential energy is any energy that's being stored, any energy that an object has that it is not currently using to achieve something, okay? So you can kind of think of potential energy as like when you've eaten a meal, you gain energy from that meal, but you don't necessarily burn through all that energy immediately, right? That energy stays inside of you so that you have it when you need to accomplish something. So that's kind of the idea of potential energy. It's energy that things have that they can then use for something useful later, okay? So that's why I want to point out this second line here. Potential energy is only useful when it's converted into some other type of energy. All right. Potential energy on its own does not do anything. It does not accomplish anything, but it is energy that the object has that's available for it to use. As we said on the last slide, this can be chemical energy like we would find in food, nuclear energy, which is pretty complex and it's what we use to power like a nuclear power plant it gets energy or creates electricity by splitting apart the nucleus of an atom. Okay, elastic energy we already talked about. Basically, the idea that if I stretch something out or bend it out of position and it wants to go back to it, that's energy that it has. And gravitational, which is our huge focus, how much energy something has based on how far above the Earth it is. All right. So potential energy, and this is a good point here. Potential energy is stored when work is used to move an object, typically against an opposing force. That's not so true for chemical or nuclear energy, but for elastic and gravitational it is. And we're going to focus in on gravity, right? When you think about it, when I do work to something to lift it up, I'm exerting a force over a distance, right? I'm picking it up. That's the force that I'm using. I'm moving a certain distance. Great. Okay. So the amount of energy that I've given it is actually equal to the potential energy it has. So the amount of work it took, or the amount of work energy it took me to lift that thing up, that's how much energy I've given to that object, and it has now become potential energy that the object has. All right, so let's talk a little bit more specifically about gravitational potential energy. So as we've said, I think 3 times now, gravitational potential energy is energy that an object has just based on how far off the Earth's surface it is and how heavy that thing is. All right, this is the only type of potential energy that we're going to learn a formula for. And the formula is actually quite simple to work with. It might look a little confusing, but it's actually not. It's, I think, one of the easiest ones we're going to do this year. So the formula is this, what's in purple here. So EP, which stands for potential energy, this is not its own variable. It is a part of this. Okay, so potential energy, which is always measured in joules, is equal to the mass of an object in kilograms times gravity, 9.81 meters per second squared. And you'll notice I'm not using negative here. The reason is that we talked about before. Energy is not a vector unit, okay? So the direction does not matter. So I'm not going to use negatives here because if I throw a negative in here, I'm always going to end up with negative energy, and there's no such thing as negative energy, all right? So we're just going to use 9.81 meters per second squared. The nice thing about this is that it's always that number. The only time we wouldn't be using this number for this formula is if we were talking about the potential energy of something on a different planet, and then I'd probably make you calculate gravity. Okay, but that's a rare kind of question, right? And then finally we go mass, so we're going mass times gravity times height, which is always measured in meters. And by height we mean how far off the ground the object is, all right? So our formula here is EP is equal to mass times gravity times height. The cool thing is that the amount of potential energy something has will always be equal to the amount of work that was done to lift that object up, all right? So whatever force I applied to move that object a certain distance, that's our work formula, however much energy I gave the object, that will be how much potential energy it ends up with. All right, and we'll take a look at that on the next slide here. All right, so I want to take a quick aside to show you guys how the work formula that we did earlier this week, work equals force times distance, is actually exactly the same formula as our potential energy formula. Right? So what we're going to do is we're actually going to take a look at this guy here. We're going to break this down and kind of tease apart what we're looking at. Right? So remember that work is equal to force times distance, but force is equal to mass times acceleration. Okay, so all I've done here is I'm saying that force is equal to mass times acceleration, and then to get my work, I would then need to multiply mass times acceleration by distance. Okay? But remember that because we're talking about that we're lifting something straight up into the air, the acceleration that this thing is experiencing is gravity, okay? Because I have to lift it stronger than gravity. So now my formula, all I'm going to do here is change this around to work is equal to mass times gravity times distance, okay? And if I'm lifting something up, it turns out that distance and height are the same thing. However high up I lift it, that's its height. That's the distance I moved it. So we can actually rewrite this as work is equal to mass times gravity times height, which is exactly the same as our potential energy formula. So whenever a problem says this much work was done to lift something up, the work and the potential energy will be the same thing. All right, it's just how we calculate them. They use the same units. So what's funny is that we're not even using a different formula than we're used for work. We're just kind of really breaking it up into its three components. We're taking that force and splitting it up into its mass times that gravity. Okay, so we're going to do 3 practice questions here. These are all on page 7 of your booklet. They're the first 3 questions. We're going to work through them. Please let me know if you have questions when we get to Thursday's class. All right? So the question here says, what is the gravitational potential energy of a piggy bank, which has a mass of 2.3 kilograms, sitting on a shelf that's 1.8 meters above the floor? As always, we want to write down what we know. The mass is 2.3 kilograms. The height is 1.8 meters. And we always know that gravity is 9.81 meters per second squared. And it's asking us to find the potential energy. All right. Our formula, as always, is EP is equal to mass times gravity times height. So all I have to do here is multiply my 3 numbers together. Okay. I'm just going to give myself a little bit of space, and then we're going to plug them in here. So this is going to be equal to 2.3 kilograms times 9.81 meters per second squared. I do not have enough room on my iPad to keep doing this. There we go. Times 9.81 meters per second squared times 1.8 meters. Okay. When I multiply those 3 numbers together, I get 40.6134 joules. And as always, it's important that we double check our significant digits. All of my original numbers here have 2 digits other than gravity. So I'm going to round this to be 2 digits. So it's going to be 41 joules total. Okay, there's my answer. I don't have a direction. I don't need to because energy never has direction. All right, this second question is actually very similar to the first one. In fact, it uses some of the same numbers. So here we have a shelf in your locker that's 1.8 meters above the floor. If your science textbook has a mass of 1.2 kilograms, what is its gravitational potential energy? That's funny. It doesn't say that the science textbook is sitting on the shelf, but let's assume that it is. All right, so let's talk about what we know here. We know our height is 1.8 meters. We know that our mass is 1.2 kilograms. And as always, we know that gravity is 9.81 meters per second squared. Okay? And it's asking us to find potential energy. Okay? So we're going to use our formula again. EP is equal to mass times gravity times height. I'm just going to zoom out a little bit so I've got a bit more space to write things down. Okay? So we're going to plug our numbers in. Our mass is 1.2 kilograms. Our gravity is always 9.81 meters per second squared, unless we're on another planet. And our height is 1.8 meters. Okay. When I multiply those together, I get 21.1896 joules. Again, I want to round my significant digits. Just like before, my original numbers all had 2 significant digits. So I'm going to round my answer to 2 significant digits. So we're just 21 joules. The one thing I want to point out about this one is if you look, the numbers in this question are very similar to the ones from the last question. The only actual difference between the numbers here and the numbers on the last question is the mass. This one is a little bit over half the mass of the last one. Okay, the other one, if you don't remember, had a mass of 2.3 kilograms, so it's nearly double the mass of this one. And notice that the potential energy is nearly half of what the other one was. So there's 2 things that potential energy relies on. The heavier something is, the more potential energy it has. The higher up it is, the more potential energy it has. So because these guys are at the same height, the only difference really between them was the weight, and this one weighs about half as much as the other one, so it has about half the potential energy. All right, this is going to be our last problem today. This is the first one that we're going to do where we have to actually rearrange our formula, all right? So it says here, if you did 565 joules of work on a 12 kilogram box by carrying it up a flight of stairs, how high is the flight of stairs, all right? A better question would be what is the height of the flight of stairs, but that's fine. So a few things, we want to write down what we know. Our potential energy is 565 joules. Now, I know in the problem it says if you did this much work, All right, we've already talked about how work and potential energy are the same. It's just the amount of energy you use to lift something up. So you might go, how do I know this is a potential energy question? It's because the work question, like the work is force times distance, has nothing to do with mass. Okay, there's no work is like in the work is force times distance. Mass is not one of those variables, which means we're likely going to need to use the potential energy question. It also says what is the height of the flight of stairs. Height shows up in the potential energy formula, not the work formula. Okay, so that's kind of how you know. Although if you did use the work formula, it'd be fine as long as you know you had to calculate the force first, like the force of gravity, the weight of that object, and then use that to find the height. But it's easier to do this with the potential energy formula because it brings it all together. All right? So our mass of this object is 12 kilograms. Gravity is always 9.81 meters per second. Oh, jeez, I keep doing that. 9.81 meters per second squared, and I don't know my height. All right, so we're going to need to rearrange the formula. As we've talked about before, our formula is EP is equal to mass times gravity times height, but now I'm trying to find height. Okay, so what I want to do, as always, is undo everything that's currently happening to height. And right now, all I'm doing to height is multiplying it by mass and gravity. The opposite of multiplying by mass and gravity is to divide by mass and gravity. So I'm going to divide this side by mg. I can do that both at the same time, okay? These will both cancel out, but I also have to divide this side by mg. So my formula, now rewritten, is h, height, is equal to potential energy divided by mass times gravity, okay? And kind of like the force and work formulas, every time we rearrange this formula, it's going to end up looking the same. It's going to be potential energy divided by the other two things that you know. One of them should always be gravity. So it'll either be, and I'll have this at the end, it'll either be H equals potential energy divided by mass times gravity, or mass is potential energy divided by height times gravity, okay? But it's always going to be potential energy up at the top. I'm just going to clear off some room for myself here. All right, so now that we have that, we're going to plug our numbers in. So our potential energy is 565 joules. And we are dividing that by 12 kilograms times 9.81 meters per second squared. Okay. When I do that in my calculator, what I get as an answer is 4.8 meters. Okay. I have the correct number of significant digits. I should only have 2 because my mass only has 2. And so that's my final answer. Okay, and I just wanted to go through the 4 different rearrangements this formula can have. This won't take long. We've already done one of them. So our original formula is potential energy is mass times gravity times height. If I wanted to find mass, what I'm going to do is divide both sides of the equation by GH. Okay, so I want these removed. So my new equation, if I want mass is equal to potential energy divided by gravity times height. If I wanted to find height, like I did in that last question, it's H is equal to potential energy divided by mass times gravity. And in the rare chance, although it can happen, that I wanted to find gravity, if I was asking you for the gravity or the pole of gravity on another planet, you would go G is equal to potential energy divided by mass times height. All right, so you'll see that in all cases, whenever we rearrange this formula, potential energy is above our division sign, and then the other 2 variables end up below. All right, so it's a nice, easy formula to play with. What I'd like you guys to do now is take time to go through the practice questions on page 7 and 8 of your booklet. They're not terribly hard. You should be able to get through almost all of them with very little trouble. The answer key is up on D2L. And stop when you get to page 8. We will pick this up in Thursday's online class. I hope you guys have a great day.